Here I have a laser. It's a helium neon laser. It's a red laser. And when I turn it on, the light from this laser is going to shine through two slits, two vertical slits in this screen here. And after going through those two slits, the light that comes through the two slits is going to shine about 6 meters that way and land on the screen that's down there, which you'll see in a second. And what we're going to do is we're going to look at the pattern of light on the screen after the light from this laser has come through those two slits. So now what we've done is we've moved the laser and the double slit about 6 meters that way. So the laser is shining through the double slit over there, 6 meters away. And then the light, after coming through the double slit and traveling 6 meters, is landing on this screen. And what we see here is a classic two-slit diffraction pattern with alternating bright and dark spots. And so this convinces us that just as microwaves are waves, light is made of electromagnetic waves. And we can actually even look at this in a semi-quantitative way. I won't claim that I'm going to do a precise measurement here, but the light is traveling about 6 meters. And now let's see what the spacing is between bright spots. If I take my ruler here and put it up there and have a look, what I see is that in 5 centimeters, I get 4 bright spots. And that means that the spacing between bright spots, or the spacing between dark spots, is about 1¼ centimeters. And so now the ratio of that 6 meter distance to this 1¼ centimeter spacing between spots is 480. And what that means is that the wavelength of this red light is 1/480th of the spacing between the two slits. And so one way of using that information is to look up from the manufacturer of the slits, how wide are the slits? And 0.3 millimeters is what the manufacturer tells us. And then you take that and you divide by 480, and you get something in the range of 600 nanometers for the wavelength of the light. So this is a way of measuring the wavelength of the light. The other way of using this, which is actually a much more general sense of what diffraction is used for, is to say, well, we know what the wavelength of the red light from this laser is. It's in fact 633 nanometers. And so that means we use this diffraction pattern to learn something about the structure of what the light is diffracting through. And here we have the simplest possible example. The light is diffracting through two slits, and the structure of those two slits, well, that's how far apart are they? And so I take 633 nanometers and I divide by that ratio, 480, which was the ratio of the 6 meters to the 1¼ centimeters, and I learn that the slits are about 0.3 millimeters apart. That's much more, gives a much better sense of how diffraction is often used, because diffraction is used to learn about the structures of small objects. In this case, the small object is two slits. We'll discuss other examples in the next video. And you know, by sending light whose wavelength we know through those two slits and studying the pattern, we learn that the slits are 0.3 millimeters apart. We're going to do this with a more complicated example, one step more complicated example in the next video. And to foreshadow that, I will point out that there's something in this pattern that we haven't discussed yet, because yes, there's dark spots and bright spots evenly spaced, and that's what we know the math for. That's what's analogous to what we did with the microwaves. But it also seems like the bright spots go dim right about here. And then the bright spots go dim again right about here. And the bright spots go dim right about there. Bright spots are dim here, dim here, dim there. And the bright spots are brighter in the middle, and then here, and then here. So there's something else in this pattern. There's some more information here that we haven't yet learned how to interpret, and we're going to come back to that in the next video.